Hey guys, Spencer here. What you just saw earlier was simulated images using a StyleGAN in order to come up with all these really cool ideas from already created images, and you get a new image based on those previous images. Now that was using StyleGANs, and that is based on GANs. So what is a GAN, you might ask? A GAN stands for Generative Adversarial Networks, and it is essentially two neural networks beating each other up, trying to get one edge over the other, and it will come to the point where one of the neural networks can't identify whether or not your data that's coming in is real or not in terms of a binary classification. Now let me use this analogy. In the United States, we have the Secret Service. Besides protecting the President of the United States, one of their primary roles is to identify real from counterfeit money. In the GAN world, the Secret Service, they will be known as the discriminator. And within the neural network world as well, the counterfeiter is known to be the generator. So the generator, or the counterfeiter, is always trying to find ways in order to improve their methodology to bypass all of the security concerns from this Secret Service and be able to use their currency within the overall United States. The neural network generator is always updating its weights to identify what is the best weights to use within the given architecture to make sure that the data that they are outputting, whether or not the dollar bills are fake or counterfeit, can be distinguished from the eyes of this Secret Service. So you essentially have two neural networks, the generator and the discriminator, duking it out. You have the discriminator that's trying its best to distinguish data that are real or fake, and you have the generator that is outputting these types of data, whether it be real or fake, to try and improve its weights to make sure that whatever data that comes out, it is indistinguishable in terms of a binary classification, indistinguishable from whether or not the dollar bill, for instance, is real or fake. And we want the output to be very close to 0.5, where it's just a coin toss and the discriminator can't tell the difference. That is essentially what a GAN is. Now, throughout this entire video, there'll be two sections. One section is going to go a little bit further into depth on how the architecture of a GAN is set up. I'll be doing that in Python, and the second part is going to be referring to transfer learning, and that is the output that I've sort of done earlier in this video with all those simulations, where I've already used already built architecture and framework in order to output whatever I would want, since many of those models are already trained and I don't have to spend any dollars on those resources, etc., etc., etc. So let's begin with the first one and just understand how to put everything together and how to get a GAN built. Now this is just a snapshot on what my directory looks like, but in the particular notebook I'll be using is the art Python notebook, and I'll be referring to the folder with abstract data. And these data are images from, I believe it was like WikiArt or some Kaggle. It was one of those two resources, but this has thousands of images inside of them. Now, within here, I just wrote some code on if you have a GPU, you can check that out. If you can also list what type of GPUs are available in your machine, check out your TensorFlow version. These are some of the packages that I use in order to make sure that all of my images are squares in terms of the length and the width. And so all my images were 299 by 299, but I just wanted them to squeeze it down to 256 by 256 just for divisibility by 2. But you can honestly just leave that alone. And over here, this is where I'm referring to the images. These are the image channels. So my images are three-dimensional, so they have 3 dimensions. But some of your images might be 2-dimensional, and that is a grayscale difference, and so you would have to be vigilant about whether or not your data have more than 2 dimensions and what to do about that. So you have to make sure that all your data they all share the same data dimension characteristics. And so this is one of the ways that you can sample your data. Just make sure like you squeeze everything together into like a square format if it's not already a square. Flatten out the images and then normalize them Just standard stuff, and then write this down, numpy.save. You can put that as a numpy array, and then you can utilize that for your future data usage. Now let's go over to the Google Colab. If you're not familiar with Google Colab, it's essentially like a really neat free Google Cloud resource that you could utilize for just testing out your small stuff. If you want to scale out and scale up, you can always just buy more resources and run more complex models that take up a lot more time. So let's jump over there real quick. Now I jumped over to my Google Colab. This is my Google Drive. I essentially just transferred the abstract NumPy data, well, 11 gigabytes, pretty much took up my entire free space. Put it somewhere inside of my folder structure over here. Now you can refer to that to your Google Colab notebook. First thing before you even get started, you want to click on your runtime, and you want to change your runtime to GPU instead of just like none, which is the default, and you can utilize its own GPU framework on the Google Colab. And let's run this. I believe they only give you one GPU. Yeah, one GPU, and they also tell you what type of GPU devices that are in play over here, and it is XLA GPU. Yeah, I mean, stuff like that if you're interested in that sort of thing. Now here, this is where you want to connect. Now over here, this is where you want to make sure you are connecting your Google Drive to your Google Colab, and this is just like mounting essentially like external hard drives. You can think about it like that via the cloud. And now if we refresh this over here, notice that this popped up and I have my entire folder structure up and ready over here. And you can easily refer to that pickle file over here, and then you can just refer to that for further use. These are the packages I'll be using, just Keras extensions and some numpys to actually load the data over here. For the purposes of this video, I'm not going to be like running everything. I'll just be explaining the components. So first part here, latent dimension. You can think about this as the random noise generation. This is just a value you can be plugging into your generator. You'll be using that value to just output like an image. Stuff like that. So that's where the default value is. You can change that to wherever instead of like 0 or a negative number, just like a positive integer. The neural network configuration, in a different video I'll be going over like what the epochs and batch sizes are, but this is a more advanced video, but this is what I have going on here. Batch size of 32, epochs of 30,000. Sample period, we have 200, so for this particular case, every 200 epochs I'm going to be saving an image and storing that somewhere over here, so I can just take a look at what's going on. So every 200 epochs I'll be saving an image. Image size, you can change this whatever dimension it is. In this case mine was like 256, but I'll leave that as 128 just for if I have other images to go through. I can easily change that. Image channels, if you have 3, then you have colors. 2 I believe is like grayscale, and if you don't have any, actually no, if you don't have any dimensions image channels in your sets, then you know that you're working with like grayscale images, and you can easily check that out to see how many dimensions are inside of your image using the PIL package, PIL. This is me just loading the data. I'm not going to run this. It crashes my RAM and disk over here, but yeah. These are some basic functions. If you want to keep on running this overnight, Google Colab, I think they kick you out after 12 hours. But every, like, I guess 8 to 12 hours, you want to save your progress and load your progress, and then just keep on running it whenever they give you more time to run your stuff. So over here, this is where the generator is. This is courtesy of a article I was reading, Medium. I just copied and pasted a generator over here, and I was running this this generator, and it was all right, but it took up a lot of time. But I'm not going to be running all of this right here. But anyways, yeah, this is the generator. So using my previous example, this is the neural network that is trying to counterfeit money in order to try to trick the Secret Service into thinking that their money is, you know, real or not real. And so this is probably the more important pieces, but the discriminator is also very important in distinguishing the fact whether or not the data that's coming in is real or fake. And you can easily change these structures. I'm going to be using a different structure later to demonstrate what your outputs could potentially look like based on transfer learning. But yeah, you have a generator and you have a discriminator. Now this is where the really, I guess, like the nuts and bolts is going to be. This is where you define, your typical image shape. You got your sizes, your length, width, and number of channels. You got your optimizer over here. You want to build your discriminator based on the image shape, which is just running the function up above. From earlier, we'll be using a binary cross entropy, which is essentially just binary classification, determining whether or not the data that's coming in is either fake or real, and that's where the accuracy metric is going to come into play. And then you have your generator. You can be building your model. This is the input that you'd be passing into your generator. So think about your Latin dimension. That's all it really is. It'll be generating some value here. Make sure that you turn off your discriminator trainable is equal to false. Otherwise, your entire model, you're training like two different instances of your neural network. And if you train your discriminator, then your generator is not going to go anywhere because it's always going to be at ground zero, because the discriminator will know whether or not your data is false or true just based on how the architecture is set up. So do make sure that it's set to false, the weights are set to false, so that it's not continuously updating. You only want to update your generator. And then over here, this is your prediction. This is where you just pass in your generator function to your discriminator, and then you combine your models where you have your input shapes over here, and then you pass in your fake prediction, and then you just want to compile everything together. That's the very first step. And this is sort of self-explanatory. I mean, it's just coming from a TensorFlow package, the model package, and you can think about it as initializing the weights with the fake prediction and the inputs that are coming in, and then you want to compile everything, like re-update the weights within the model. Just compile that based on your given loss function, and you want to optimize based on your optimizer, which I'm using Atom over here. Now, next part, I have ones and zeros. And this piece over here, ones always symbolizes, I'm gonna write this right here, symbolizes the values that are true. And this is values that are false. And this is just the predictor value that's going to be pasted onto whether or not your incoming data is true or false. And then your architecture will know whether or not it's successfully distinguished between two different data, whether or not it's true or false. And then these are just the arrays where you can just print them out later. You can create a path that stores all of your output data, and this is where the epochs will then run. So I'm just like setting it really low. You can set this to like more than like 10. Like I think I had epochs of 30,000 up above, but you can change that to whatever you want to be. So we have two sections. One is the discriminator portion, and one is the generator portion over here. The discriminator over here, it's right here. This is where we are picking randomly, however, I think it's like 32 random photos over here. Gets those indexes, gets those random images, it associates those random images to the real images over here. And then we want to generate some fake images where we have the noise values over here. Fake images, this is where you just pass in your generator model. You predict based on that noise. So you have two separate steps over here, and then this part is where the discriminator is going to be happening. Over here, discriminator train on batch. These are just built-in functions over here, and I believe that's that train on. Yeah, that was a typo over here. But anyways, you essentially have your different loss values for the real and for the fake. Take the averages between the two, and you have a recorded value that is just going to be appended to the arrays that we have up here for the losses. Same thing, similar, happens for the generator. We have the noise, we have the generate loss, and then for here within Ian Goodfellow's paper, the father of this architect, he ran it twice, and he did that for some interesting reason. I couldn't really determine why, but in his algorithm, he did it twice, and I believe it was to, I don't know, make it better, I believe. But yeah, bottom line is he ran it twice in his overall paper, and he saved the losses over here. Well, I saved the losses over here. And then at the end of the day, whatever epochs you want to do, if you want to save it at your second epoch every 2 of them, or if you want to save your images, you can always do that as well. And that is basically the entire algorithm here. It should output images. Well, actually you have to write some code over here. Write code to save images, which isn't that difficult. It's like np.save or something like that. And you save it over here, and then you can, just use the eye test to determine whether or not that particular image looks real or fake, right? That's really all it is over here. Now let's get back to the transfer learning. Now, this is the StyleGAN that utilizes other people's works and architectures to really develop something really cool. You can always add on to this ongoing process and ongoing work, but there are essentially 2 libraries or GitHub repositories that I've used, and that is dvscuhltz, which he can be found over here for one of his notebooks, and NVIDIA. As always, I mean, NVIDIA was the one who developed the StyleGAN, so I'm utilizing these 2 folks, or one company and one guy's resources in order to develop this really cool application. So one thing I want to make a tidbit on, I was doing the calculations, and to calculate how to create your own individual network that you can develop cars or artwork or cats for that instance. I'm gonna need about 8 V100s for about 48 hours, and that's about $1,200.
Ain't nobody got time for that.
I don't have $1,200, so I'm not going to be creating a network from scratch, but I will be going through the processes on how to actually do that, and I'll be actually also applying ways on how to transfer learn, how to use other networks in order to just get a sort of out of the box type of a algorithm or architecture, and just run some really cool stuff. So over here, just follow the basic instructions that I had earlier. You want to mount your drive over here. Make sure you connect to your My Drive so that you are in a base directory. And then you can follow these instructions over here. I got this from dvscuhltz. I copied and pasted some of his code on over as well, related to his default generator function. It was run generator, and there's a run training option over here, and there's some tweaks on that, and that's pretty much the only difference between the 2 libraries of NVIDIA's and dvscuhltz. But yeah, you want to make sure you run this, get all of your code up to date, and there are 2 things I want to highlight. One, let's start over here. So the function gdown, that's just Google download. It's downloading, or this is just downloading a pickle file on related features that you can use as a starting point, and that belongs in the pickle file over here, and this is what it is, the inception features over here. The next part, this is where the actual transfer learning is happening, going into the results section over here for under pre-trained networks. I downloaded a car and a cat architecture, and this came from NVIDIA, straight out of NVIDIA from this Google Drive over here, and these are all of the public known pickle files or the architectures that NVIDIA has. You can do cars, you can do cats, churches, and FFHQ, which is essentially the faces of people. And that's really cool. That's one of their trademark things over here. And then what you want to do, you can do this manually. You can download individual instances on where this on whatever file you want to pick, and then you upload this to wherever Google Drive you want to upload your stuff to, and then you just reference this into your further code down. And so this is my results file, and this is under 00001 pre-trained. Cool. And then you want to make sure you actually run your TensorFlow version. It's going to be about 1.14. I believe that's the version for StyleGAN2. And this is where it sort of diverges in terms of utilizing the out-of-the-box architecture versus your pre-built or your custom-made architecture. And this is where your customization will come into play. So instead of having a pickle file or like a NumPy array, you can easily just upload all of your JPEG images or your PNG images to a specific datasets file, datasets over here. And it's arbitrary, but you want to make sure you reference wherever your records are at, and you will run their function dataset_tool.py. It's essentially just converting all of your images into a TensorFlow record, which it will then use to start training over here. It'll start using those images, the TF records. It will start training those into its huge network that it has over here. The G underscore is the generator function, and the D is the discriminator. So you can check out how large these neural networks are, and it takes forever to run, but that's expected for a neural network. And then this should output a pickle file, which will then be like, just house all of the corresponding architecture, the weights, and you can just pick up from there, and then you always update a certain pickle file. And that's really all it is for the StyleGANs, and then you can keep on training until you get the results that you so desire. So over here, this is just essentially using the function out of the box. So not necessarily even have starting off with a data set, but you can easily just start off with one of their built-in functions, which I mentioned earlier for here under the pre-trained networks. For this case, I just did the cats. I already did the car one, but in this case, I did the cats. Over here, you reference that network. You can set the seed to whatever you would like. And then if you take the magnitude of these, or to just take the difference between the two, absolute value it, that's how many images you're going to get. And then you can choose whatever images you would want from these seeds over here. And just for an example, you can open up that file. You can open up like the very first one, and then you get a cat like this, or you can go to the second one, another cat like that. That's really cool. So you can pick whatever images over here, and then you can go further down. You can now run your run generator function on to generate the latent walk, and this is essentially using the same exact like architecture from the transfer learning. And now the only difference is like you have the frames and you have your seeds over here. The seeds just correspond to what position of the actual image file that you want to use in order to create your overall MP3 or MP4 file. And this came from the dvscuhltz or Mr. Schultz. Really cool. Then you get all these images, and then you can convert them to frames using the FMPEG, 24 frames per second. And then you just reference the newly created generate latent walk over here, which was generated by the function all the way. Come on, over here to run generate latent walk. You just refer to that, and then you convert all those to a frame, and that will then convert to a file called I called it cat_walk.mp4. And that was over here somewhere. Yeah, catwalk. You can double click that, and then you have it downloaded. Then yeah, you got your cat looking like this. Oh, that was like human. Okay, yeah. So you got your cats. It's moving from point A to point B, and it's doing all of these really cool transition pieces. Really cool and awesome work by Mr. Schultz. And you can always apply this to different structures. If you have car data, or if you have human faces data, you can use a human faces built-in function. Or if you want to generate your own, you can create like your cityscape works, or whatever other abstract works of art there are, and generate something that no one has ever seen before. I'm glad that you guys made it to the end of this video. I really do hope that you enjoyed on how a GANS came to be, and probably give you maybe some further inspiration. If you're an artist, for instance, you can always create and code along a generator function, or a GAN function that will then create art, and maybe you might have further inspiration to create further masterpieces. And I hope to see them in the future. If you like this video, please make sure you like and also subscribe, turn on those notifications on. I got much more content coming down the pipeline, and I hope that you enjoy those videos as much as I do. Thank you for watching, and I hope to see you in the next one.